Hi, today I want to address a global issue that carries significant consequences in terms of property loss, injuries, and even loss of life. Arson, the deliberate and malicious act of burning properties, is a serious problem we face. It is categorized by three key elements: the burning of properties, an incendiary origin of the fire, and the intent to destroy the properties. Proving a sign requires determining the cause of the fire, which can be challenging due to the potential destructive of evidence. However, with a significant investigation, we can uncover significant evidence to establish the cause and bring justice to those responsible. Arson demands our attention, and by understanding its element and conducting through investigation, we can combat this destructive crime and mitigate its devastating impact. Today, I bring to your attention a recent and unfortunate fire incident that occurred at Wisma Jackel in Section 07 Kuala Lumpur, Malaysia. Wisma Jackel is a renowned garment and textile establishment in the country. The fire reportedly started at approximately 7:20 am and continued until it was brought under control at 3 p.m. Eventually being fully extinguished after several more hours. In response to this emergency, nearly 90 firefighters are swiftly dispatched to the scene. I regret to inform you that during the operation, one firefighter sustained minor injuries from hot stone treatment and was subsequently taken to the hospital for further examination. Thankfully, there were no casualties reported to this incident. The fire resulted in the complete destruction of Wisma Jackel, conflicting significant loss upon the Jackel Group. Preliminary estimates suggest that the loss incurred amount to almost 100 million ringgit Malaysia. The Selangor Fire and Rescue Department (JBPM) promptly mobilised its canine dog detection unit to the scene to determine if any element of arson were present or its accelerant were used. However, their investigation had led them to believe that the cause of the incident was a short circuit. The loss of Wisma Jackel is undoubtedly a devastating blow, not only to the business but also to the community. This incident underscored the importance of implementing robust fire safety measures, conducting regular inspection, and maintaining electric system to prevent such occurrences.
According to the situation, a few chemicals that can be potentially found is gasoline, which contain toluene and benzene through the sample carpet, wood, ash and soil. We can also found another chemical which was identified as ethanol and acetone. I would like to introduce you to an extraction method called solid phase micro extraction or SPME, which is utilized for the extraction of gasoline from fire debris samples. SPME is a technique that offers several advantages, including rapid extraction, non-destructiveness, and absence of solvents. When analyzing volatile compound present in fire debris samples, such as accelerants like gasoline, SPME proved to be an effective approach. This method involved the absorption of volatile accelerant into the thick layer of silicon, which is then analyzed using gas chromatography. The process of SPME consists of two main steps. First, the volatile compounds are absorbed from the sample matrix into the silicon coating of the SPME fiber. This absorption occurs selectively, allowing for the extraction of specific analytes from the complex sample matrix. Next, the The adsorbed analytes are transferred from the SPME fiber into the chromatography inlet system through a process known as liquid desorption. The amount of analyte absorbed during SPME depends on factors such as the thickness of its polymer coating and the distribution constant for the analytes. This selective and sensitive technique enables the detection of trace level of analytes within complex matrix, such as fire debris samples. While SPME proved to be a powerful extraction method, it is important to note that the SPME fiber needs to be replaced frequently to maintain optical performance. This ensures the reliability and accuracy of the analysis. Solid phase microextraction of SPME is a valuable technique employed for the extraction of volatile compounds, including gasoline, from the fire debris samples. Its non-destructive, solvent-free nature, coupled with its selectivity and sensitivity, make it preferred method for analyzing trace level of analyte within complex matrix. However, it is essential to regularly replace the SPME fiber to ensure reliable results.
I want to discuss about a method called solvent extraction, where it is used for separating compounds based on their solubility. Solvent extraction involves transferring a compound from one liquid phase to another. By utilizing the difference in solubility, one component of the mixture dissolves in the solvent, while the other component is separated through filtration. An ideal solvent for this process has a low boiling point and does not chemically interfere with the substrate. However, finding a solvent with all of these ideal characteristics is very challenging. It is crucial to use a solvent that provides a high efficiency, even if it may not possess all the desired characteristics. In fire debris analysis, a nonpolar liquid solvent is typically employed because ignitable liquid residue found in the sample are nonpolar in nature. However, it is important to take note that more polar ignitable liquids such as ethanol and acetone may be present in the sample. Therefore, the choice of solvent should be based on the specific analytes being targeted. Solvent extraction offers several advantages. It can be operated at lower temperatures compared to other methods, which can help and prevent the compound from degradation and alteration during the extraction process. However, one drawback is that solvent extraction often requires a large volume of solvent, making it a solvent-intensive method. Furthermore, during solvent extraction, emulsion formation can occur, resulting in stable mixture of solvents and the sample. This can prolong the extraction process and require additional time and effort to effectively separate the two phases. Solvent extraction is a valuable method for separating compounds based on their solubility. While it offers advantages such as operating at low temperatures, it does require a significant amount of solvent. It is worth noting that emulsion formation can occur, adding to the time required for the extraction process. By carefully selecting an efficient solvent and addressing the challenges associated with this method, accurate and efficient compound separation can be achieved.
I would like to introduce you to a method called headspace analysis, which is a quick and effective technique for analyzing small, well-contained fire debris sample. This method involves heating the fire debris sample to release any volatile accelerants into the headspace above the sample. A headspace analysis offers several advantages, with one of the key benefits being it efficient in terms of time. When compared to the solvent extraction, headspace analysis requires less time to complete. This time efficiency makes headspace analysis a preferred choice when quick results are needed. It is important to note that headspace analysis is particularly suitable for volatile compounds. Chemicals such as gasoline and ethanol, which is commonly found in fire debris, fall into this category. Since volatile compounds easily vaporize, they can be readily detected and analyzed using the headspace analysis. Considering the volatile nature of compounds of interest, headspace analysis emerges as the most suitable sampling method. Its time efficiency further strengthens its appeal over solvent extraction, especially when expedited analysis is required. However, it's crucial to acknowledge that headspace analysis has its limitation. This method primarily focuses on volatile compounds, meaning it may not capture non-volatile components present in the sample. To ensure a comprehensive analysis, complementary techniques like solvent extraction may still be necessary. Headspace analysis is a valuable method for quickly and effectively analyzing volatile compounds in fire debris samples. Its time efficiency made it preferred choice over solvent extraction when rapid results are desired. However, it is essential to keep in mind that this method is limited to volatile compounds and may not capture non-volatile components.
I want to discuss the application of GCMS in the analyzing volatile sample, specifically liquid or gas sample that has been collected. GCMS is a powerful technique used to detect and identify various compounds present in the sample. To prepare the gas or liquid sample for GCMS analysis, two common methods are employed, which is SPME and solvent extraction. This method helps to extract the target analyte such as gasoline, diesel, lighter fluid, which are often associated with the injectable liquid residue in the fire investigation. During the GCMS analysis, it is crucial to set a specific parameter. Given the boiling point of the sample, which typically ranges from the 90 degrees Celsius to 200 degrees Celsius, a temperature gradient is required for running the sample effectively. Additionally, since the sample have low flash point and are prone to burning in the presence of oxygen, they must be carefully injected into the GCMS instrument. The choice of the carrier gas is also important, as it needs to be inert to prevent interaction with the analyte. Moreover, a standard DB-GC column with the minimum depth of 12 meters is commonly used for separation and analysis. By analyzing the result obtained from GCMS, a chemical fingerprint can be established, aiding in the identification of the primary cause of the fire. It is important to note that the presence of the injectable liquid residue does not directly prove the arson case, but it does provide the valuable information about the fuel source that either caused the fire itself or contribute to its spread. GCMS offers several advantages. It is highly sensitive, capable of detecting the trace amount of compound. However, it is also susceptible to noise disturbance in the presence of the contaminant. Additionally, each run of the sample takes a relatively short amount of time, resulting in a shorter total runtime compared to HPLC. However, it is worth noting that the use of the inert carrier gas makes its run more expensive and subsequent replicate run can further increase the cost. GCMS is a powerful analytical tool for analyzing gas and low boiling point liquid sample. It sensitively allows for the detection of even small trace amount of compound, while it offers the short run time compared to HPLC. The use of the inert carrier gas can contribute to the higher cost. Through GCMS analysis and chemical fingerprint can be established, aiding in the identification of the fire main cause. I would like to introduce you to HPLC, a powerful technique used for analyzing liquid and solvent samples, regardless of their volatility. HPLC offers several advantages, and it commonly employed in the fire debris analysis. Unlike GCMS, HPLC does not involve the temperature in its operation. Liquid and solvent samples prepared through the method like SPME and solvent extraction are placed inside the HPLC instrument with a specific parameter. The analytes of interest in the fire debris are often injectable liquid residue, such as gasoline, diesel, and lighter fluid. The volatility of the sample does not affect the result in the SPLC, as it does not rely on the temperature for the separation. Injectable liquid residue are non-polar hydrocarbon, so the mobile phase used in the SPLC need to be polar, with the stationary phase need to be non-polar. This ensures the effective separation and analysis of the target compound. Through HPLC analysis, a chemical fingerprint can be established, providing valuable information for identify the main cause of the fire. It is important to note that the presence of the injectable liquid residue does not directly prove the arson case. However, it does help identify the fuel source that either caused the fire itself or contribute to its spread. One of the significant advantages of SPLC is its applicability to a wide range of the sample. As long as the solution can be prepared, SPLC can be used to analyze it. While the runtime in SPLC is slightly longer compared to GCMS due to the liquid state and relies on the mobile phase, it still offers the efficient analysis. GCMS may not be sensitive as the GCMS, but it is capable of detecting trace amount in its sample to a certain degree. Furthermore, SPLC tend to filter out noise better than GCMS, resulting in clear result. Replicating SPLC analysis is relatively straightforward. Replicating SPLC analysis is relatively straightforward, as the mobile phase is more cost-effective compared to GCMS. This makes it easier to conduct replicate run for quality control purposes. SPLC is a valuable technique for analyzing liquid and solvent samples in the fire debris analysis. Its versatility, ability to filter out noise, and easy to replication contribute to its widespread use. While not as sensitive as GCMS, SPLC can still detect trace amount and establish a chemical fingerprint to identify the main cause of the fire.
Next up is the method chosen. In summary, GCMS is chosen as a suitable method. This is due to the accuracy of the results that we can obtain. It is important when it involves court cases, since trace amounts left over from a fire would be impossible for anything other than a GCMS to detect. These data will be utilized to indict someone. Despite the possibility that the noise from the complicated matrix could become an issue, this can be resolved with an excellent extraction procedure or by the use of effective calibration curves. In conclusion, a number of sample preparation techniques, including solid phase microextraction, solvent extraction, headspace analysis, gas chromatography, and high-performance liquid chromatography, can be used to analyze the fire incident that occurred at Wisma JAKEL in Section 7. Every method used here is appropriate for the many types of analytes or samples that were taken at the scene of the occurrence, including carpet, wood, ash, oil, and dirt. To determine the fire's fuel source, GCMS is employed on volatile substances, including petrol, diesel, and lighter fluid. A temperature gradient is necessary for accurate analysis, and the samples are produced using SPME and solvent extraction. In order to prevent contact with the analytes, the carrier gas is inert. The outcome gives a chemical fingerprint and assists in determining the fire's primary cause. Without temperature variations, HPLC analysis liquid and solvent samples with an emphasis on typical ILRs like petrol, diesel, and lighter fluid. Polarity is a requirement for both the stationary phase and the mobile phase. The findings give a chemical fingerprint and pinpoint the fuel source as the primary cause of a fire, not an intentional act. Based on the sample and analytical procedure, we can infer that the incident is either connected to a criminal element or the opposite, depending on the recorded result.